Okay, when working with beats, we have, for the examples we're looking at here, let's say we've got two sound waves. Now they're both sound, so they've got the same speed. But they could have different frequencies. Now, what effect is that going to have? Well, the reason why beats here are kind of special is first, it's so easy to hear this on its own. If you've ever tuned a musical instrument and you have something like, oh, I'm playing this note, and you've got some test note, some test system that you're judging that against, you can align it in that form. Now, what's cool about that is you've got those two waves, and if you have both waves, D1, for example, is equal to some amplitude times the sine of k1x minus omega 1t plus maybe some phase shift D2 is the same. For ease of use, let's just go ahead and say, you know what? Let's say that either the phase shift is 0 for both, or they're the same. That'll all even out in the end anyway. And then if you want to add those two together, then, okay, we can break those together because I've got sine 1 and sine 2. And if I have sine alpha plus sine beta, then I can use a trigonometric identity. The book does it. It's right in front of us. To get to the point of a displacement is equal to, if, let's give both of these the same amplitude, because hey, why not? Then I've got, okay, that comes into 2a times the cosine of omega 1 minus omega 2 over 2 times t times the sine of omega 1 plus omega 2 over 2 times t. And let's see. So notice what happens is I've got two things right here. So let me draw this. Whoops. Now, if I take that sine function, this section right here, at any given point, that's the sine of the average where did you write this? The sine of the average angular frequency times t will give me a plot to look something like this, to the limits of my admittedly very small artistic ability. Now, if we're looking at sounds like, say, omega 1 was like 320 hertz, and omega 2 is like 317 hertz or something, then the average one is going to be, well, let's call this 316, if I'm just making up numbers. So the average would be 318 hertz. So that would be a pretty high frequency, so the period would be short. So we have these sections between us. But what I have right here is the cosine of the difference in those two over 2 times t, or I'll get some outer shell at here, delta omega, or if I were to say F1, F2, and delta F would then be 4 hertz. That would be a much lower frequency, so a much longer wavelength. And the end result that I'm going to get is that this is going to act as a shell, basically, for, this is the frequency I'm going to get based on the average frequency, but that's going to be constrained by this function of the difference between them. So what you'll hear is, you'll hear a note sounding, in this case, at 318 hertz, but that note itself is going to be oscillating, so you'll hear an additional beat pattern of 4 beats on top of that. It's hard to show, unfortunately, to have the microphone pick up. Let's see. Let me. Well.